We are starting the day with a wonderful keynote address by Angelo from Zetta Scale Technologies. He is the CEO and CTO of Zetta Scale and has been the force behind the DDAS operations with ROS2 and just trying and making ROS2 better for all of us to use. So, what better than hearing from him himself or how Zetta Scale is working with Zenoh and how is it making our lives better? I think folks who have attended the workshop know pretty much about it. So, Angelo, all yours.
Thank you.
Come on, guys. He deserves a louder clap. Come on. Thank you. Thank you so much.
Okay, can you hear me? So, Namaste, Bangalore. It's my greatest pleasure to be here. Some of you know that I have a long history with India, and it's always a pleasure to be here. But let's go in presentation mode, and let's get started. Okay, here we go. I cannot, yeah, now everyone can see the slide. Okay, so in the next 40 minutes or so, well, it was 40, now it's already 5. What's going on? In the next 40 minutes, we'll be trying to understand a little bit more what is Zenoh, for those of you that are new to it, and more importantly, why we came up with Zenoh, okay? So a little bit about me. By formation, a telecommunication engineer. I have a PhD in computer science. I've been working in distributed systems since I was literally a young kid because that's what I've always loved. And I'm one of the 3 persons that actually started the standardization in 2002, not 20, 2002. And actually at some point decided to leave that working group around 2015-16 to start a new protocol, which, well, it's actually Zenoh, as some of you know. As of today, I lead the Eclipse Zenoh project. I'm on the Eclipse board of directors, Zetta Scale CTO, and actually co-founder. And as we heard yesterday from Jeff, there is the OSRA, and I have the pleasure also to be one of the representatives in the TSG at OSRA. So, robotics, it's really about, in a way, the mechanics, right? If you want to make a parallel with the human body, as a roboticist, typically we have to deal with, making sure that we represent the mechanics, the movement, and so on and so forth. The other element is the brain in our human body, and that's typically the realm of artificial intelligence. But a brain and a body alone, don't give you much unless you put a nervous system. And the nervous system is what actually makes everything work together, right? We tend to forget that many of the things that we can do because we have a body, right? Because we have a brain, and more importantly, because we have a good, in fact, an incredible nervous system that connects everything else. And so if you make the parallel between the human body and what we do as engineers, for a moment, putting aside souls, because we can discuss that after my keynote. But if we remain to the more tangible aspect, right? The nervous system is essential and is what makes the system between something working great as we humans and something clumsy like a Frankenstein. Okay, and the nervous system, usually you don't see it unless it doesn't work. When the nervous system doesn't work, nothing else works. And that's the same in robotic system. If communication doesn't work, all of a sudden, it's a mess. And so today we're going to focus on communication because that's our domain. And communication is the realm, in fact, of distributed system. And what I want to do in the next, let's say, 5 minutes is an accelerated course on the history of distributed computing. Because I think it's very important to understand where we started and when we landed, and why, and what was the evolution that took us there. Now, we've been building distributed system for a long time, but in the early day of distributed system, the communication abstraction were actually bespoke and part of the business logic. The first step, when we started actually building frameworks that were independent of the business logic, was in the 80s. And actually, that was seminal work from Bruce Nelson, PhD, at CMU, where he introduced the concept of RPC, Remote Procedure Call. So RPC were introduced in 81, and eventually the first commercial implementation, guess what, was in a Xerox Spark system, for those of you that recall Xerox. And RPC were about abstracting the location of a function, right? I'm able to trigger and call a function whether it's in the same process or on another process and potentially across the network, okay? So that was the first abstraction that was built that was not integrated in business logic, and it was the first building block back then that could be used to actually build, distributed system. Then in the 90s, with the growth of object orientation, eventually came Corba. I'm pretty sure that some of you have heard about this name. A few of you have probably used it, but actually Corba is still heavily deployed even in telecommunication network today. And Corba took beyond, took or elevated the concept of RPC to object orientation. So the abstraction of Corba were distributed object, right, with state and operation or methods that you could call without caring if these objects were running on the same host, on the same process, or perhaps across the network. But once again, the main abstraction is still client-server relationship, and we are still in the realm of RPC. But is RPC enough, right? Think for a moment the kind of system we were building in the 80s and the 90s. Those were mostly transactional system, right? System that were dealing with, mostly banking system or system that were compute intensive, right? Literally, what we wanted to do was to be able to trigger computation here and there, and not much more than that. And while we were still building air traffic control system and other more data-intensive system, for those kind of application, the infrastructure had not emerged, was still very much tied into the business logic. Why? Because in reality, whenever you build a distributed system, you need something to deal with data in motion, right? Moving things around, like your sensor data that you want to distribute, something to deal with distributed computation, and something to deal with storage. So RPC actually isn't enough. And in 1993, there was a seminal paper that if you have not read, I highly suggest you go back and read it, that was published at SOSP 93, and that introduced the information bus. That was introduced by a company that was called Technotron, which eventually was renamed into TIBCO. And I think that might sound familiar because TIBCO stands for the Information Bus Company. And this was the birth of PubSub, okay? The argument of the paper was that actually to build systems that are easier to evolve, easier to integrate, is essential to have, aside from RPC, this mechanism that allows you to produce and consume data in an anonymous manner. And in their case, they were using subject to represent the kind of data that could be produced or consumed. 1 year after, right, as this need of dealing with distributing data was increasing, and let's say that now this framework that were becoming more efficient were also adopted by application that before couldn't afford to adopt an horizontal communication framework because of performance or because of footprint. They were improving in performance. They were now needed to deal with data in motion, and that led, for instance, to the standardization of the first PubSub service, which was the Corba event service. Okay, that was in 1994. And it's interesting to observe because Corba built PubSub based on an RPC abstraction. Was that great? Well, that came with some complications because essentially you were trying to build an anonymous abstraction starting from a client-server abstraction, and the implementation of the Corba event service were essentially centralized. So they had some performance bottleneck, and they were introducing a single point of failure. Those limitations led in early 2000 to the standardization of another form, let's say, technology, DDS, that was trying, while providing the PubSub abstraction, to remove the limitation that were present, for instance, in the Corba event service and some other protocol or some other PubSub implementation that were built on top of RPC. So what DDS did was to take PubSub as a primitive, okay, and to ensure that you could do PubSub in a completely decentralized manner. Please keep in mind that when we did DDS, back then, DDS was addressing essentially defense and aerospace system running in local area network that were well-dimensioned, where you had multicast, and you could assume that the packet loss was very, very low. Those were the operational assumptions that we had in DDS, which for sure are not the assumption that you have when running on a Wi-Fi. This is why the protocol struggles on Wi-Fi. It wasn't just designed for it, okay? Now, let's take a quick step back and let's compare Corba and DDS. So we started in distributed computing with RPC. We tried to do everything with RPC, and then we saw that obviously you can, and there is, by the way, a paper that shows the equivalence in terms of expressiveness of PubSub versus RPC. But then, trying to build PubSub with RPC brings some limitation. So we built PubSub as a primitive abstraction, but then we were missing the ability of representing distributed computation. We were missing RPC. Recall the TIBCO paper. You need actually both in system. And that's where one tried to put RPC on top of DDS. And that actually, yeah, you can do it, but it's not very efficient because you're trying to build something now that is not at all anonymous, that is about me communicating with you, right, on a system that is completely anonymous. And that was creating more problem than it was solving, okay? So, more technology were deployed and developed. In Java, you had Java RMI, which was just the Java version of Corba. You have OPC UA, which is, again, an extension of Corba, but in the Microsoft sauce because they were using DCOM, and so on and so forth. And if you fast forward into early 2010, some other change happened. All of a sudden, right, we started having system that instead of being just embedded system or just enterprise system, now we're spanning from the microcontroller up to the data center. And building this system was a mess because, first of all, there was no technology able to run from the microcontroller up to the data center. And as you see, technology were either providing you RPC as a primitive or PubSub and then building everything else on top. And so either one or the other use case wasn't well supported. Not to mention the ability of dealing with data at rest, okay? Because again, data moves in PubSub, but at some point I need to store it. And once I store this data, I lose location transparency, which then is very problematic because how do I keep track of where I've stored the data if I need to know the location? This seems, we give this for granted, but this is one of the consequences why most systems that span from the microcontroller up to the data center today are kind of forced to store data in the data center. Because if you decentralize, then how do you keep track where you have stored your data with current technology? And all those struggles actually were the creative force, because in order to create energy, you have to create struggle, which is differential of potential, right? If there is no differential of potential, there is not energy. But those struggles were the energy that led to the creation of Zenoh. So when Zenoh was designed, the original goal were essentially two, but we ended up addressing three problems, the third one by accident. So the first problem that we wanted to solve was we want to have a protocol that can run efficiently from the smallest microcontroller and perhaps constrained network up to the data center. No protocol could do that because it's actually pretty hard. We didn't indeed do it at a snap of a finger. But unless you set ambitious goal, things are not very interesting. The second problem that we wanted to solve was we wanted this protocol to allow you to keep data stored wherever you wanted on the system and transparently query it from anywhere else. So in other terms, we wanted a protocol that not only could distribute data, right, so PubSub, but also would support geo-distributed queries. Okay, you keep data where it makes sense in your mobile, but your friends can query it even while I'm in Bangalore, while he's sitting in Paris or in Palo Alto. Okay, that was the key idea. And actually, the result was, as we will see, that we also managed to address and to solve the problem of distributed computation. Now, we worked on Zenoh for a few years as a closed, let's say, R&D project in our R&D group. And then eventually, it was unveiled to the world, what was it? Actually, the 10th of November, 2017. So there you see the first public commit of Zenoh, of the very first version of the protocol, with the vintage logo. Okay, so what is Zenoh? Zenoh is kind of a one-of-a-kind protocol because it's the first PubSub query protocol. Okay, so it provides you with PubSub abstraction, but provides you also with this concept of distributed queries. And by using these two kind of abstractions, so PubSub and distributed query, we're able to represent data in motion, data at rest, so source of data, so storages around the network that we can query, and computations, as we will see, okay? And these abstractions are location transparent. The advantage of location transparent is that it's very easy then to deal with load balancing and fault tolerance. We'll quickly touch on it. The other important thing is that Zenoh had, since the very beginning, built-in support for shared memory and zero copy. And that was done, again, the Zenoh way, without any centralization. So it's a distributed shared memory, as we discussed quickly during the workshop. Quick note, Zenoh is an open source project, but it's not just a project on GitHub with an open source license. Zenoh is part of the Eclipse Foundation, which gives you all a series of guarantees. First of all, it ensures open governance, transparent governance, meritocratic governance, because any of you, if you provide sufficient contribution, right, can participate to a committer election and become a committer. And all these processes are supervised by the Eclipse. And for the user, you have another guarantee that every Eclipse release is checked for IP violation, for patent violation, and provenance, okay, as well as licensing. So there is a concept of a bill of material, and so your guarantee as an end user that an Eclipse open source project, it doesn't violate patents, has not stolen software from some other place, and doesn't have any strange license that might create problem to your commercial software. Close parentheses. Okay, let's go back to Zenoh. So what does it mean to be a pub-sub query protocol? So it means that Zenoh has really two primitives. And again, when you see this diagram, don't think topology. Here, it's logical flow of data. We will discuss about the topology that are supported later on. But essentially, Zenoh allows you to do data distribution, so pub-sub, and to trigger query. So query is literally a get operation in Zenoh. I can do a get where I provide a key expression because everything in Zenoh works with keys. And then it's the Zenoh protocol that decides where to route this query. Queryable will be triggered, they will execute, and they will return, as you see in the animation, a stream of data, okay? A finite stream of data. And then the protocol allows you to know when a queryable is done responding and when all the queryable that have triggered are done responding. So those are the basic mechanisms. So obviously, the matching between publisher and subscriber are done just by doing intersection between key expression, okay? You can think of key expression as representing set of keys. Let me show you some code because the API is super simple. This is how you open a Zenoh session. And Zenoh sessions are also used to negotiate lots of protocol properties. You can even negotiate the sequence number resolution. So if you are on a microcontroller running on, let's say, BLE, you probably want to negotiate 1 byte sequence number resolution because that's plenty for you, okay? So that's how you open your session in Rust, and you can use both synchronous or asynchronous API, and this is how you put data, okay? You don't even need a publisher. The API couldn't be simpler, I think. Okay, we put lots of effort in designing clean API. Technically, publisher in Zenoh don't exist as network entity, but you can still declare publisher, okay, in order to, let's say, allow us to do some optimization, which I can't explain right now, but happy to talk about after, and then still produce data using a put operation. You can declare subscriptions through the declare subscriber operation, and then a subscriber in Rust is a stream. So all of a sudden, you can operate over a subscription that is consuming asynchronous data as if it was a container that you're iterating sequentially, which makes your code very easy to read, avoids inversion of control, and in general, right, makes much easier to understand the business logic that you are creating. And if you are into functional programming, then of course, with streams, you can use higher order programming and get wild with it. Let's move to queries. So when issuing a query, Zenoh takes, in fact, a selector. Here I'm showing you the short story. So I'm giving you a trivial selector, which is just a key expression. But in a full-blown selector, you have a key expression, a question mark, and then you have a query expression that depends on, it's a DSL for queryable, okay? So when you issue a query, Zenoh will look at the key expression, and then we'll look at something else called the target. And depending on the target, we'll decide to how many queryable it needs to route this query, okay? So target can be best matching, all, and all complete. So in the case of all, trivial, all queryable whose key expression intersect the key expression of your query will be triggered. And again, what does it mean, a key expression associated with a queryable? Is nothing but a kind of contract the queryable makes that tells, look, if you're looking for any data whose key matches this key expression, you can come to me because I'm like an oracle that knows how to answer those kind of queries, okay? You can also visualize queryable as well, where you can go with a saw to take water, and the water that you take, is labeled with keys that match that given key expression. You can use the best match. In that case, then we trigger one queryable that is the best matching, and in terms of routing is the closest for you. So depending on where you are on the network, it might trigger different querybles. And then you can query all complete. I won't discuss in details completeness, but that has to do with your queryable essentially not having alls in its data set. So there is no key inside the set expressed by the key expression for which it cannot give answer. And for those of you that are into replication or high reliability system, that's important for implementing quorums. So you can easily implement quorum with this mechanism in Zenoh. I'll close the parenthesis on quorum. So how can you use this? Well, in several ways, but let me show you one creative manner. Suppose we wanted to do MapReduce. So I want to represent multiple executor that will have to compute in parallel the sum of an array by taking portion of that array. So in this example, I have three queryable whose key expression are compute parsum executor 1, executor 2, and executor 3. As an application, I can submit a query saying, please compute parsum star, and I pass as an attachment the array. This array, if I use target all, will be distributed to all of the queryable, which will compute the partial sum, reply to me, and then I will be able to reduce that computation to the sum, okay? That's just one example on how to use queryable, but there are more, which I'll show you in a moment. Again, in code, this is how you submit a query. It's just a get operation, okay? This will trigger querybles, and it's nice because you don't know if the data is being computed or if it's being retrieved from a storage. Because if you think about the storage, like InfluxDB, MariaDB, RocksDB, whatever, we represent those in Zenoh like the combination of a subscriber and a queryable. Because all of a sudden the queryable represents the ability of reading from the storage, while the subscriber is just the writing side of the storage, okay? And just to sum up, if you think for a moment, right, what we need in distributed system, which is the ability to deal with data that is moving, like your sensor data, with distributed computation and with distributed storages, in Zenoh we can support all of those. PubSub, naturally, it's a primitive. Distributed computation with queryable. And distributed storages, they are just represented as a combination of a subscriber and a queryable. And in Zenoh, you already have plugin for plenty of storages. Okay, let's move now to the protocol stack. When we designed Zenoh, we wanted, as I said, to be able to run from the microcontroller up to the data center. And so when deciding where we could afford to sit in the protocol stack, we decided that we wanted to be able to run as low as the data link. Which means that the only things that we need in Zenoh, it's something, literally a link, that allow us to send bytes from A to B. Okay, where A to B are directly connected, because that's the role of the data link. That also tells you that Zenoh does its own routing, and we will see that in a moment. And it's named-based routing, as in named-based networking protocols. Now, as we can run on top of data link, it's not surprising that today Zenoh can run over Bluetooth natively, it can run over serial links, but it can also run at higher layers on the ISO OSI protocol stack. So we can run on top of UDP, we can run on top of TCP, we can run on top of QUIC, and we run on top of VSOC and adding a new link, as we call it, it's actually pretty straightforward. It's just not even 100 lines of code, okay? The protocol is the minimal protocol overhead is very small. It's a handful of bytes, and that is very important because on constrained network, the MTU is very, very constrained. And in terms of topology, you have no topological constraint. You can do peer-to-peer, let's say a la DDS, okay? Assuming that every peer can directly talk with every other peer, but you can also do mesh. This is very important where you have radio communication. Radio communication, I cannot assume that through my radio signal, I can reach every other application. Usually, I need to communicate through a mesh, and sometimes, carrying forward messages on behalf of other applications. We can have clients which are applications that say, hey, I'm not powerful enough, to mesh up and to carry data or move data around on behalf of other applications. I need someone else to do that for me. And that someone else can be a peer or could be a router, okay? Router in Zenoh are software routers. They are very lightweight. Many robotics companies run a router inside the robot. And as you will see, in the ROS utilization, actually you have a router by default in RMW. That tells you how lightweight and efficient it is. And obviously, router can be deployed across the system, within a factory or across the internet, as we usually do, to provide you, as we will see, with an internet scale Zenoh network, okay? Because that's how we can actually scale really your system. So once again, no topological constraint. That's very important because you decide what is the right way of to communicate between your application and whether it has to be peer-to-peer, whether it has to be meshed, or perhaps if you want to route, either because of scalability or because you need indeed to reach across the internet and at a large scale. Other important things, any application can communicate over an arbitrary number of links. So the same communication could be talking serial with one other application, QUIC with another, Bluetooth with another, and TLS with yet another, as an example. So just to put topology in perspective, in the middle you have Zenoh, then you have MQTT on my left side, right, with a broker-centric architecture, and DDS on the other side. So, on one extreme you have DDS, only peer-to-peer. On the other extreme you have MQTT, broker-centric, and then you have Zenoh, which removes all topological constraint. Because again, as an architect, you should decide in the given system segment what is the right topology that fits. Other important aspect, we talk about links and how we can easily support different kind of data links or networks and so on and so forth. But Zenoh was built with plugin in mind. So in Zenoh, you can plug third-party protocols. So I guess some of you have been using the ROS2 plugin or the DDS plugin in Zenoh, but we have plugin for third-party protocols. So we can transparently bridge DDS to Zenoh, we can transparently bridge MQTT to Zenoh, and so on and so forth. And we have plugin for third-party databases. So we have plugin for S3, Minio, InfluxDB, RocksDB, and so on and so forth. I will go very quickly now. The protocol does lots of things for you. It does automatic batching, which is very important for network utilization. It has automatic fragmentation. That's very important. You can send payload of arbitrary size. And it has a prioritization. That's very important when you deal with real-time traffic. And by the way, the Zenoh RMW will be able to do this, and I'll explain briefly later on how, even in the context of ROS2. There are two Zenoh protocol implementation, one in Rust and another one in C. The one in C, we call it Zenoh Pico and addresses a microcontroller. The one in Rust essentially is the one that is used by most users, and the one that is used, in fact, for all the infrastructure. Why? Because of the security guarantee that the Rust programming language provides. You are not forced to use Rust because we have plenty of API. We support C, C++, Kotlin, Java, TypeScript, Python, and Go is about to come for those of you that use it. Other important thing, you can write application in C++, and at compile time decide if you want to target the microcontroller version or the general purpose version. and even the CAPI are essentially identical, modulo some addition that we need on the embedded version just to deal with threading on microcontrollers. Plenty of supported OS, both on the desktop as well as on the microcontroller side. So you can run these on Arduino, ESP32, Zephyr, but you can also run on automotive target like AUTOSAR Classic. And if you look at performance, those are numbers that are taken from a paper from NTU, which was comparing the performance of Zenoh, peer-to-peer, pub-sub, Zenoh, publisher, router, subscriber, that's the violet line, DDS, Kafka, and MQTT. Notice that the axis is logarithmic, both the X and the Y. And if you look, for instance, at 8 kilobytes payload, you will see that Zenoh is at almost 70 gigabit per second on a 100 gigabit per second network, where DDS is around 18 gigabit per second. Adoption. So Zenoh is increasingly used in automotive. So actually here you see the first run of an autonomous car being driven by Zenoh at the Indianapolis circuit. Here you see Zenoh actually used on board and off board in the Lucy autonomous train. This is in Germany. So that's a train manufactured by Thales and deployed in Deutsche Bahn, as well as Zenoh used inside Carla with an autonomous driving stack. There is a recommendation to standardize Zenoh as the protocol for intelligent transport system communication. So in the slide you have the reference, it's a good read. And again, Zenoh is used within the Eclipse SDV, adopted by General Motors U protocol, which is their infrastructure for EV and autonomous driving. And in other verticals, you find Zenoh in Internet Analytics platform. Actually, we power 3 blockchain, one of those being Solana, industrial automation, medical devices, and defense and aerospace application, ranging from air traffic control up to a fighter jets application. Amazon has identified Zenoh as actually the most promising protocol for next generation IoT. And now the question is, what is Zenoh role in ROS2? Okay. So, as you might know, right, and as I've explained, ROS2 users have had some challenges due to the design space of DDS when trying to use ROS2 with the underlying DDS RMW on, let's say, wireless network, or when trying to scaling it out, okay, because of its discovery overhead. That has caused so much pain that at some point there was the decision to investigate and look for alternative protocol. So there was a study. If you have not read the study, please read it because it's extremely well done throughout. And I think it gathers the typical problems as well as deployment scenarios for concerning networks, target, and the requirement that are key for next generation robotics. They surveyed multiple protocols, I would say the key protocol available on the market. And in the end, the result was that Zenoh was the one that came across as the most fit for addressing the requirement of modern robotic application from a technical evaluation. But actually, even the community poll was asking for Zenoh. Why? Because many companies were already using Zenoh. In fact, dropping a router in the robot and communicating Zenoh outside of the robot while keeping DDS just inside, using one of our protocol plugins. So as a result, Intrinsic committed, and thanks to Intrinsic, to develop the RMW for Zenoh. And as you learned, it will be tier 1 by the next Zenoh release. And that was facilitated actually by the ROS architecture, because ROS has a modular architecture. In ROS, you have the RMW that abstracts the communication layer. And as such, it was relatively straightforward to plug Zenoh as an alternative RMW to the existing DDS implementation. There was some choice taken, okay? Some choice were taken because, for instance, for encoding, DDS RMW ROS RMW were DDS based, which uses CDR for data encoding, so the same was kept for Zenoh. Does that mean that you are forced to CDR? Well, perhaps in the future, you will be able to support other encoding because Zenoh doesn't force an encoding, okay? Then publisher and subscriber in ROS are mapped naturally to Zenoh publisher and subscriber, although you know that the publisher is just some optimization on the wire. And service server are just mapped to one queryable, which is quite nice because it makes sure that you have, first of all, a one-to-one interaction and slashes already quite a bit of discovery data. By the way, if you've seen some of the number of discovery data in Zenoh, now you understand that by construction, Zenoh divided discovery by 2 because there are no publisher, okay? Just to give you an idea. And then there are other reasons why typically we have 90% less discovery data than DDS. Actions are mapped on 3 services and 2 topics, okay? Because this mapping is done at RCL level. Ideally, one day we'll be able to do a slightly different mapping and map also action on a single queryable. And then for entity graph discovery, we use a Zenoh mechanism called liveliness token, which again, we described in the webinar. The slides are already available on LinkedIn. Not the webinar, we described on the workshop. In terms of the architecture, this is how the Zenoh RMW will be deployed. You will have a router running on all of your robot, and that's the default deployment. This router will be used in order to configure all the communication outside of the robot and to facilitate discovery inside your ROS nodes. Notice that nodes will be communicating peer-to-peer. We showed all kind of startup order and start and restart during the workshop, just to reassure people that this is not a single point of failure. I mean, if it fails, your node will continue to communicate. If it comes back up, then you will resume connectivity to the rest of the world. I want to pause a moment on this architecture because it's very important to understand this router. It's a key integration point because that allows you to decide what gets out of your robot, at which frequency, and with which protocol. Because maybe I want to use security just when communicating outside and not necessarily inside of my protocol. And again, we really dissected all the use case during the workshop. All the material is available online, and there is an entire repository with a series of exercises you can go through to understand the advantage of this. And there is a later talk today that will actually go quite deep on it. So the Zenoh potential, and we are actually, that's, I think, oops. Oh, that slide doesn't want to come up. Let's see if it comes up. Oh, here we go. The Zenoh potential that will wrap up is the following, right? This protocol has no limitation with respect to running from the microcontroller up to the data center. So as we saw already 2 days ago at the workshop, right, we were able to run easily, right, on a laptop or across the internet, right, with pulling up subscription from topics that I was publishing in my laptop, from Vivek laptop across some router that we're running in Singapore as an example. But this is the potential that we have with Zenoh, right, which is unlocking your robotics application and making it finally simple, easy peasy, as a British would say, to really have this transparent communication, right, from the microcontroller up to the data center. Teleoperation becomes trivial, and the lots of application that you have trying to build will be unlocked. So wrapping up, Zenoh is one-of-a-kind protocol that unifies data in motion, data at rest, and computations. It's the only protocol that gives you the ability to run from the microcontroller up to the data center with no topological constraints. And it's extremely easy to use, as you saw with respect to the API that we presented. So thank you very much. The slides are already available online by now. So just scan the QR code because that will take you to my LinkedIn page where there is a LinkedIn post with the slides and a link where you will be able to download the slides. Thank you very much.